Okay, students. So far we have discussed what mixtures are and what solutions are and the components solvent and solute. And also we have an idea about the solubility of different solutes in a solution or in a solvent. Now we will move on to a new topic, composition of a mixture. Now you must be wondering why I have two completely different figures here. Now as you can see, these are things that you use in your day-to-day life. Now this is a cup of tea. Let's say even if you don't drink tea, you will drink milk. If you are a person who drinks tea or milk with sugar, what happens if we put about 10 teaspoons of sugar to 1 cup of tea? Obviously, the sweet will be too much. The tea will be too sweet that you can't drink it. And if you are a person who needs sugar for tea or milk, if you don't have sugar, if you forget to add sugar to milk or tea, then also it will be difficult for you to drink it. What if there is too much of tea leaves? So all these have to be considered when making tea, or for that matter making milk or any other food substance that we eat at home. The same way, this is another example. I have shown a color palette, for example, shades of green. Now you all know when you mix blue with yellow, you get the green color for your painting. So this you have been doing from your smaller grades. But you all also know that by mixing different amounts of blue and yellow, you can get different shades of green. And into that, if you add a little bit of black, you might get a very dark green. And if you add a little bit of white, the green will become lighter. So likewise, you can mix paints in different ways, the colors in different ways to get different shades for your purpose. So like this, we can think of many examples. You put something in excess. For a food item, we add a little more water to dilute it, or say in the lab, when we are preparing a solution, when you take too much of the solute, we can add a little bit more water, increase the volume and make it to our requirement. Or if there is not enough of a solute, then we add more solute. So here, what do we mean by more, less, not enough, too much? These are all qualitative words that refer to composition of a mixture. So qualitatively, we say too much or not enough. The same way, we need to get different shades. So all these are possible by combining substances in a proper quantity or in a certain proportion. So the mixing of substances in correct amounts. This is something that is necessary for us in our day-to-day life. The same thing, if we give it in a quantitative manner. then we call it the composition of mixtures. Quantitatively we say this amount of, than saying 1 teaspoon of sugar, we say 3 grams of sugar. 1 teaspoon, a person can have a half a teaspoon, a flat teaspoon. Another person can take a heaped teaspoon. So that will be confusing. Instead, if we say 3 grams, 5 grams, 100 grams, those are very, very specific values. So as we have discussed here, quantitatively measuring the amount of components in a mixture is the composition of a mixture. This is very, very important to us. So first, although you know what composition is, you have a qualitative idea. Now again, quantitatively, we will observe what this composition is or why that is necessary to us. To do that, we will discuss an activity. Activity. Study the composition of a mixture. For this, we need two materials, mainly the beaker. In a beaker, we will need to take distilled water or water. We are not going to use the solution. We are going to observe the solution. So, it doesn't have to be distilled water. We can use the normal water as well. Then this is the solute that we need. From the picture, you can identify this is condensed. That is the common name, potassium permanganate is the chemical substance. So what we will do is, we will weigh two different amounts of potassium permanganate. Say 0.2 grams and 0.4 grams. So quantitative values. Then we take two identical small beakers. To that we take equal volumes of water. Say 50 centimeter cubes or 100 centimeter cube. To that, to one beaker containing water, we add the 0.2 grams of potassium permanganate. To the other one, we add the 0.4 grams of potassium permanganate. And we have to mix it well by stirring with a glass rod. Then we place it on a table side by side and observe the physical properties. Say the transparency, the color of the solution. You all know when we dissolve potassium permanganate, although it looks like black color crystal here, what is the color you will get as the solution? A bright purple color. So we will look at the method again. Take 50 milliliters of water into two beakers. Add 0.2 grams and 0.4 grams potassium permanganate separately to the two beakers and stir well with a glass rod. Record your observation. So this is again a very simple activity. Let's do this in the lab. Okay, students. So we are going to do this activity in order to observe the composition of mixtures. So for that, I have the same solvent and solute. I have here 100 centimeter cubes of water. Although we were supposed to take 50 centimeter cubes, in order to show you all the color change or the difference in intensity of color, I have taken more water, but in both the beakers, I have equal volume of the same solvent water. And here again, I have a very small amount of potassium permanganate and a larger amount of potassium permanganate. So the same solute but different amount. Now I will dissolve the smaller amount of potassium permanganate in water. So here you can see it is a purple color solution. At the same time, I will dissolve the large amount of potassium permanganate, and when we dissolve that is also a purple color solution. But here you can see the difference in intensity of color. Although the solvent and the solute are the same and both solutions are at the same temperature, because I took less amount of solute, that is less amount of potassium permanganate, the intensity of the color of solution is less here. And when we take more solute, the intensity of the color is more. What is the reason? The reason is the amount of solute in a unit volume of solvent is less in this and more in this. So therefore, the amount of solute present in a unit volume of the solution is very important to us. That is what we will be defining as composition. And to give compositions, we have different units. But students, you all can understand that the amount of solute in different solutions give rise to difference in composition of the solution. Okay, students. So you saw the observations of the activity. We prepared 2 solutions of potassium permanganate and you observed the physical properties. How do they look like, or were you able to differentiate the 2 solutions? Yes. We had 2 beakers. I'll draw the observation here. And the second beaker, this had 0.2 grams of potassium permanganate and this had 0.4 grams of potassium permanganate. What was the intensity of the color? Here, the purple color was light. Here, the purple color was darker compared to the first solution. Both were clear, transparent solutions, but the color, the purple color of the solution where we added 0.2 grams was lighter, whereas the color intensity was darker there. Why is that difference? The reason is the amount of solute particles, that is amount of potassium permanganate in a unit volume of the solution is less here, more there. So that means the composition of this mixture or the solution is different from the composition of the second solution. Although the solute and the solvent are the same and we get homogeneous solutions. That is why we refer to them as solutions. But because of the difference in amount of solute, the composition of the 2 solutions are different. That is the conclusion we can obtain from this activity. So I can say the composition of the 2 solutions is different. That means, in brackets I can say, the amount of solute in a unit volume of the solvent is different. So this is why we say the composition is different. Now let's discuss why this composition is so important to us. When preparing mixtures of weedicides and insecticides, they must be prepared in correct composition. So here we discuss weedicides and insecticides. When we say side, some substance or a chemical substance used to destroy or control a living organism. So weed is a plant that destroys the growth or retards the growth of the crop. Say a paddy plant, weed can reduce the production of paddy. So weedicide is used to destroy the weeds. Insects also destroy crops. They become pests. So to control those insects, we use insecticides. So always side with the particular organism is used as the name. Weedicide, insecticide. Say there are too many weeds. So a person who is using the weedicide, normally he or she prepares it according to the specifications given in the weedicide bottle or the container. Say a small lid full of weedicide into 1 bucket of water. But this time the person notices that there are too many weeds. So he thinks, okay, I'll add 2 lids full of weedicide so that there will be more weedicide applied and all the weeds will die quickly so that my crops will be safe. What do you think will happen? There is too much of weedicide. One thing, it will go waste. It will go into the water bodies and pollute the water body. Before that, it can pollute the soil. Why? The excess weedicide can retain in the soil and it can change the composition of a soil. That might destroy the crop as well. So the person won't get the required output. Instead, all the crop might get damaged. The same way, if a person thinks, okay, weedicides are harmful, so I will use a little lesser amount. Say I'll use half a lid full of weedicide. Then what will happen? The weeds won't be controlled. So you can't use more or less of the weedicide. You have to use the given amount or the specified amount. The same for the insecticide. If there is too much of insecticide, that can pollute the environment, that can harm the other living organisms. But if you use too less of the insecticide than the specified amount, the insect will not be destroyed. So you have to use it in the correct composition. The same way, prescribed composition should be used when preparing solutions using pharmaceuticals. Pharmaceuticals refers to the tablets, the syrup, all the medications that we use. Now let's say if you have fever, if you need to take a tablet, if you are supposed to take one tablet, you have to only take one tablet. Taking two will be too much, that can give side effects, and taking half will not be enough for your particular ailment. So you have to use one tablet if you are told to use one tablet. The same way, if it's a small child, they might say give half a tablet. Now then what do? We break the tablet. Normally there is a line, we break it into half or we cut it into half. Let's say when we cut it into half, if the two halves don't contain the same amount of the chemical substance, that is the medicinal compound, then in the morning the child will take too much of the medicine. In the night the child will get only a lesser amount of medicine. Then also it's not correct, or the ailment will not be cured properly. So the full tablet has to have uniform composition and it has to be according to the prescribed composition. The same way, we might use vitamins, minerals in the form of medication. We might think, okay, instead of one, if we take two, we will get more energy or more minerals. No, that can become harmful to our body. Same way, thinking that it is a chemical substance, if we take half of the prescribed amount also, we won't get the required effect. So we have to stick to the prescription given by a medical person. Okay, the next one. Laboratory work often involves the preparation of solutions of fixed composition. Solutions of fixed composition. Like we did before, 0.2 grams of potassium permanganate in 50 centimeter cubes. If that is what is needed, we can't use the solution that has 0.4 grams of potassium permanganate. So we have to prepare the solution according to the requirement. Therefore, knowing the composition of solutions and by knowing the method of preparing these solutions properly, we can use all these substances in the correct manner without wasting substances, without coming across other issues, to get the required output or to get the wanted outcome. So therefore, the composition is very much important. So let's say, therefore, understanding about the composition of mixtures is very important in everyday life as well as in laboratory experiments. There are several ways to express the composition of a mixture. Some of those are discussed in the following sections. So we'll see what the first composition is. Composition of a mixture as a mass fraction m divided by m. You all know what mass is. Mass is the amount of matter present in a certain substance. So here we give the composition as a mass fraction. I am sure we all know maths very well. You know what fractions are. You divide one quantity by another quantity of the same type, or it can be different types. So here, since we say mass, you divide mass by mass. That is the mass fraction. Let's say, let us consider a mixture comprising of two components A and B. The mass fraction of A in that mixture can be expressed as. So the mixture has only two components, A and B. So we'll consider this as a solid mixture. So the mass fraction of A, or you can write it as mass fraction of component A, is equal to mass of A divided by mass of A plus mass of B. So mass of A is that particular component. What is mass of A plus mass of B? It is the mass of the mixture. So these two together give you the mass of the mixture. Mass of the mixture. So always we divide the required component by the total mass of the mixture. Then you will get the mass fraction. Hence, the mass fraction of a given component of a mixture is the ratio of that component to the total mass of the mixture. So, ratio of the mass of that component to the total mass of the mixture. So, is this only for component A? No. You can find the value for component B as well. How do we write that? I am sure you also can do it. Mass fraction of B will be equal to mass of B divided by, I can say, mass of mixture. What is that equal to? Mass of A plus mass of B. Or you can write it as mass of A plus mass of B. So that is the same. The total mass or the mass of the sum of mass of the individual component. So this is a very simple equation. You have to remember this equation. Now we will discuss an example. Example. 20 grams of glucose was dissolved in 180 grams of water. So we have glucose and we have water. Find the mass fraction of the components. So first I'll find the mass fraction of glucose. What is that going to be? Mass of glucose divided by, I will write as M of glucose to save space plus M of water. So what are the values? Mass of glucose is 20 grams. Always students, if you substitute with the unit, it would be convenient for you all. Less chances of making a mistake. What is the mass of glucose again? 20 grams plus water is 180 grams. So when we simplify this, what do we get? 20 grams divided by 20 plus 180, 200 grams. So here the 2 grams will get cancelled off. So what will be the answer? 1 over 10. 20 divided by 200, 1 over 10. That is the mass fraction. Here it says find the mass fraction of the components. So if I find the mass fraction of water. So although you know water is in excess, so that's the solvent, glucose is the solute. Since they have mentioned components, we find for both. So here I am not rewriting the equation. The mass of glucose is 180 grams and the total mass we have already found 200 grams. So you will get 180 divided by 200. So when I simplify 18 over 20, that will be equal to, what will be the mass fraction? It will be 9 over 10. So 1 over 10 and 9 over 10. They do not have a unit, or we say the unit is 1. That is something that you have to remember, students. So here unit equals 1, or you can say no unit, because the two masses have to be of the same unit. You can't have one in grams and the other one in kilograms. You have to have the components with the same units. So then there will be no unit, or the unit will be 1. Another thing that you can notice here, there are two components. The mass fraction of the first component, that is glucose, is 1 over 10 and the second component is 9 over 10. Now, if we consider the sum of mass fractions, what do you get? 1 over 10 plus 9 over 10. That becomes 10 over 10. When you simplify that, you get the value as 1. So always remember, students, when you add the mass fractions of all the components in a mixture, the value will be 1. So these are the things that you have to remember. The unit is either 1 or there is no unit, because the two units get cancelled off. And when you calculate the mass fractions of all the components and you add them together, the answer will be 1. So in another way, if you know the mass fraction of glucose as 1 over 10, you can subtract 1 over 10 from 1 and get the mass fraction of water. So that can be done. You have got the basic understanding of what mass fraction is. We will do some more calculations. The first question. 100 gram of the solution contains 5 gram of the solute. Give the composition of the solute of this mixture as a mass fraction. So here I will say mass fraction of solute. What is that? Equal to mass of solute divided by what? Mass of solute plus the mass of solvent. Here we have the mass of the solution. So I can write the equation as mass of solution. Earlier we wrote it as mass of A plus mass of B. I told you all that is the sum of all the components. So it is the mass of solution. So if we substitute the values now, 5 grams of the solute in 100 grams of the solution. The units get cancelled off. You get 1 over 20. 5 divided by 100, when we simplify, you can give the answer as 1/20. Or else you can simplify it and give the answer as 0.05. That is also okay. But since it is the fraction, we can leave it as a fraction. I'll move on to the next question. When 250 gram of salt solution was weighed accurately and all the water in it was evaporated, 10 gram of salt was left. The question is given in a different form. Here 250 gram of solution, and from that when they evaporated the water, 10 gram of salt was left. Indicate the composition of salt in the solution as mass fraction. So here mass fraction of salt. What is that going to be? Mass of salt divided by mass of salt solution. So they have said 250 grams of the solution. So where do I write that? Here it is the solution. And what is the amount of salt remaining? 10 grams. So it's 10 grams. So these two cancel off. We get the value as 1/25. That is the mass fraction of salt in the solution. What is the unit? There is no unit or unit 1. If you are asked to calculate the mass fraction of water, what can you do? 1 minus 1/25 will give you the mass fraction of water. By always the sum of mass fractions of the components is equal to 1. Now we will move on to another type of composition. Composition of a mixture as a volume fraction. So here the quantity has changed. Earlier it was mass fraction, now it is the volume fraction. So V over V, to denote that is volume fraction. Volume fraction is used to indicate the composition of a mixture when both of its components exist either in the liquid state or in the gaseous state. And remember, when both of its components, both have to be in the liquid state or the gaseous state. If you have one in the solid state, then of course you can't apply this fraction. In a mixture containing two components A and B, the volume fraction of A can be given as follows. So here we can write volume fraction of A. What should we write here? Volume of A. A divided by volume of A plus volume of B. The two components. What is that? Equal to the volume of the mixture or the solution. So when you add them together, you get the total volume of the mixture. Accordingly, the volume fraction of a given component of a mixture is the ratio of the volume of that component to the total volume of the mixture. So this is something that you all have to remember. So how do we write the volume fraction for component B? The same way, we have to say volume fraction of B, volume of B. As I told you, this is V over V. So V of volume of B, volume of A plus volume of B. Again the total volume. Now we'll look at an example. Example. A solution of acetic acid was prepared by mixing 25 cm cube of vinegar with 75 cm cube of water. Calculate the volume fractions of vinegar and water. So you all know the main component of vinegar is acetic acid. So that is why here they have said a solution of acetic acid was prepared using vinegar. So to find the volume fraction, we can write volume fraction of vinegar is equal to what? Volume of vinegar divided by volume of vinegar plus volume of water. Why? We need to find the total volume. So volume of vinegar is 25 centimeter cube. And again it's 25 centimeter cube plus volume of water is given to you as 75 centimeter cube. So what do we need to confirm before substituting? We have to check whether all the units are same. Here it's all the same unit, so no problem. Directly you can add, so it becomes 25 centimeter cube divided by 100 centimeter cube. The centimeter cube gets cancelled off. 25 divided by 100, that will be 1 over 4. So does this have a unit? No. Same way, we'll calculate the volume fraction of water. I don't need to rewrite the equation because you have written it already here. But instead of vinegar, it should be water. So here volume of water is 75 centimeter cube divided by 25 centimeter cube plus 75 centimeter cube. So when we calculate the value, the units cancelled off. 75 plus 25, 100. So 75 divided by 100 is 3 over 4. So what can you notice here? Same as the previous fraction. The volume fraction has no unit or unit equals 1. Why? When you divide centimeter cube by centimeter cube, it becomes 1. So no unit or unit is equal to 1. So if we add up the two volume fractions, what will you get? Let's say here we have 1 over 4 and 3 over 4. So here the sum is equal to 1 over 4 plus 3 over 4. That will be 4 over 4. What is that equal to? 1. So always the volume fractions of all the components when added together give you the value 1. So that is also something you have to remember, students. Sum of the volume fractions of all the components is 1. So these are common to both mass fraction and volume fraction. The unit is 1 or no unit, and the sum of the volume fraction of all the components is equal to 1. We look at examples. A solution of final volume 250 centimeter cube was made by adding distilled water to 25 centimeter cube of ethyl alcohol. What is the volume fraction of ethyl alcohol in this solution? So here you can understand the question. They are making a solution of volume 250 centimeter cube. For that, they take ethyl alcohol 25 centimeter cube and add distilled water to get the total volume. So, to find the volume fraction of ethyl alcohol, volume fraction of ethyl alcohol, that is equal to volume of ethyl alcohol divided by volume of solution. That is the volume of alcohol plus water. But here they have said a solution of final volume. So if we substitute the values, they have taken 25 centimeter cube of alcohol and the final volume is 250 centimeter cubes. If we simplify the values, 25 divided by 250, that will become 1 over 10. The units get cancelled off, so you get the volume fraction as 1 over 10. What if they ask you to find the volume fraction of water? 1 minus 1 over 10. So as a note, I will write that here. Volume fraction of water can be found by subtracting 1 over 10 from 1. So you will get the answer as 9 over 10. Why? The sum of the volume fractions of the components is equal to 1 and there is no unit. We'll move on to another example. How do you prepare 500 centimeter cube of an aqueous solution of acetic acid of composition 1 over 25? A different type of question. 500 centimeter cubes aqueous solution of acetic acid with a composition of 1 over 25. When they say aqueous solution, that refers to water. A solution where the solvent is water. So here we have to take acetic acid, that is the solute, liquid component, and water, the solvent, that is also a liquid component. So we have the composition as volume by volume. So here we can write V over V, volume fraction of acetic acid. That is the equation we know. Volume of acetic acid divided by volume of solution. So if we substitute the values, the volume fraction is given to us 1 over 25. we don't know the volume of acetic acid. So, I will put that as V. We know the volume of the solution, that is 500 centimeter cubes. So, if I rearrange it here, 1 over 25 into 500 centimeter cubes will give you V. So, from this, if we simplify 25 and 500, it's going to be 20. So, 20 centimeter cube will be equal to V. That is the volume of acetic acid that is needed to prepare this solution. Therefore, an acetic acid solution with the composition of 1 over 25, V by V, is obtained by measuring 20 centimeter cube of acetic acid accurately and adding water to make the final volume up to 500 centimeter cubes. So, for this, we will need a measuring cylinder. We will discuss all these glasswares. Measuring cylinder to measure the volume correctly. Then to prepare the solution, we will use a volumetric flask that is available in different volumes. Here, since we need 500 centimeter cubes of solution, we will use a volumetric flask of 500 centimeter cubes. So, that is how we prepare the solution. These glasswares are used to prepare solutions with accurate composition. That will be discussed later in the unit. Next one. This is another way of expressing composition. The composition of a mixture as a mole fraction. I am sure you are familiar with this term, mole. The amount of substance present in any matter, that is expressed in moles, and the SI unit of mole is also mole. You are familiar with all these calculations from your grade 10 work. The mole fraction of each component of a mixture containing only two components A and B can be expressed as follows. So, here we can write mole fraction of A will be equal to mole of A divided by mole of A plus mole of B. Same way, if it is the mole fraction of B, mole of B divided by mole of A plus mole of B. Thus, the mole fraction of a component of a mixture is the ratio of the amount of moles of that component to the total amount of moles of all the components in the mixture. That is the definition for mole fraction. We can write this using symbols as well. You know the symbol for moles is N. So, here we can write this as usually mole fraction is given the symbol X. XA is mole fraction of A, that is equal to simple N of A, moles of A divided by moles of A plus moles of B. So, this is a way of writing the equation for mole fraction. Again, will you have a unit? No. What is the sum of all the mole fractions? it will be equal to 1. So you have to remember all those. I will include that also here. No unit. Why? The mole and mole will get cancelled off. And sum of mole fractions of all the components is 1. With that, we will look at some examples. What is the mole fraction of sodium hydroxide in a solution made by dissolving 40 grams of sodium hydroxide in 180 grams of water? So normally they can either give you the moles and ask you to find the mole fraction. Here I have given this question so that you can try to recollect how you calculate the number of moles. I am sure all of you all know that, but still we will do this calculation. So to find the mole fraction of sodium hydroxide, we need to know the number of moles of sodium hydroxide as well as the number of moles of water. So here, how do you calculate number of moles? That is mass over molar mass. How do we write that? N is equal to simple M over capital M. Normally, they will give you the molar masses of the elements. Here, I will tell you all the values. Sodium is 23, oxygen 16 and hydrogen 1. So, those are the molar masses of different elements that you need. So, first we will find the number of moles of NaOH. The mass is 40 grams. And to calculate the molar mass, sodium 23, oxygen 16 and hydrogen 1. What is the unit here? Grams per mole. So that will be equal to 40 gram divided by 23 plus 16 plus 1, 40 gram per mole. When you divide, you will get the answer as 1 mole. Gram and gram get cancelled off. The mole minus 1, you take it up, becomes mole. So 1 mole. So same way, number of moles of water. 180 grams divided by water is H2O. So 1 into 2 plus oxygen 16 grams per mole. Again 180 grams over 18 gram per mole. When you add 2 plus 16, 18 grams per mole. That will be equal to 10 moles. Now you know how to calculate the moles. We have calculated the number of moles. Then what do we do? Mole fraction of, or I will write it down since it's the first calculation. Mole fraction of sodium hydroxide is equal to NaOH divided by NaOH plus N water. So here you will get the values. We have calculated the number of moles of NaOH is 1 mole, and that is divided by 1 mole plus number of moles of water, 10 moles. So you will get the value as 1 over 11. 1 plus 10, 11. The moles get cancelled off. So the mole fraction of sodium hydroxide is 1 over 11. What is the mole fraction of sodium hydroxide in a solution made by dissolving 40 grams of sodium hydroxide in 180 grams of water? So this is the mole fraction. So we will move on to the next calculation. Calculate the mole fraction of water in the previous example. Now you all know two methods. One method we can say mole fraction of water. Directly we can substitute number of moles of water divided by number of moles of water plus number of moles of NaOH. That is going to be 10 moles divided by 10 mole plus 1 mole. So that will be 10 over 11. The mole and mole will get cancelled off. Or what can we do? Another method. You know, sum of all the mole fractions of all the components equals 1. So I'll write that here. Sum of the mole fractions of all the components equals 1. So therefore, to find the mole fraction of water, we can say 1 minus 1 over 11. 1 over 11 was the mole fraction of sodium hydroxide. So then you will get the answer as 11 minus 1 over 11. That is 10 over 11. So either you can do it this way or this way. Both are same. But this is possible when there are two components. If there are three components, to find the mole fraction of the third component, you need to know the mole fractions of the first two components. Then only you can find it using this method. So we will move on to the next one. The sum of mole fractions of all the components in a mixture is 1. We have seen that. The sum of mass fractions or volume fractions of all the components in a mixture is equal to 1. I have explained that as well. There are no units for the mass fractions, volume fractions or mole fractions of a mixture. So there are no units, and also the sum of the mole fraction, volume fraction and mass fraction of all the components equals to 1. The composition of a mixture expressed as a fraction can also be expressed as a percentage or as parts per million. So if we say a percentage, anything multiplied by 100 will give you the percentage. Like calculating the percentage of your marks. So here, if we want to find the mass percentage, what we need to do is we multiply the mass fraction by 100. Then you will get the mass percentage of a particular component. Same way, if we need to find the composition as parts per million, we refer to it as ppm. There also we multiply the fraction by 1 million. Why we say parts per million? How many parts of the particular component is present in 1 million parts of the solution? That is what we mean by parts per million. So both of these can be calculated. For example, if we take component A has a mass fraction of equals 1/5. So if we calculate the percentage, we multiply the fraction by 100. So that will give you a value of 20%. Mass fraction 1/5, mass percentage 20%. The same thing if you want to give it as parts per million, then we write it as ppm, that is equal to 1/5 into 1 million. That will give you 200,000 ppm. 1, 5 and 10 can be simplified to 2, so 200,000 ppm. Usually this is a very high value for ppm if the amount of the component or the solute is very small. Then we go for the ppm unit. Similarly, you get the parts per billion, ppb unit also. But we won't need it for calculations. So again, I will do one example related to this for you all. 20 grams of dolomite contains 12 grams of magnesium carbonate. When we say dolomite, that is a naturally existing substance that contains magnesium carbonate and calcium carbonate. So we take 20 grams of the dolomite sample. In that, 12 grams of magnesium carbonate is present. Calculate the mass fraction of magnesium carbonate and express it as a mass percentage. So first, they want us to find the mass fraction of magnesium carbonate. You all know the chemical formulae. So, magnesium carbonate is MgCO3. So, that will be equal to mass of magnesium carbonate divided by mass of the sample. So, that is, we have 12 grams of magnesium carbonate in 20 grams of the sample, that is dolomite. So, that will be 12/20, 6/10, so 3/5. When you simplify, gram and gram get cancelled off, 12 and 20 becomes 3/5. That is the mass fraction. Then how do you find the mass percentage? M/M percentage, that is mass, or you can say mass percentage of magnesium carbonate. That is equal to mass fraction into 100. So here the mass fraction is 3/5 multiplied by 100, 5 and 100. If you simplify, this becomes 20. So 20 into 3, 60, and we have to use this percentage sign. So there is 60% magnesium carbonate in this dolomite sample. That is 20 grams of dolomite. Now we will move on to the next one, that is expressing composition of a mixture in terms of mass volume fraction. So far we discussed mass fraction, that is mass over mass, mass of solute divided by mass of solution. Volume fraction, volume of solute divided by the volume of solution. Then we discuss mole fraction, mole of the particular component divided by the total number of moles of all the components in the mixture. So in all three, both the quantities were the same quantity. What you had on top for solute and the solution. But here we consider the mass of the solute or the component and the volume of the solution or the mixture. This expresses the mass of solute contained in a unit volume of a mixture. Mass of a solute contained in a unit volume of a mixture. 1 decimeter cube of G1 solution contains 5 grams of sodium chloride. Find the composition of sodium chloride in it in terms of mass over volume. You know what G1 is. A salt containing solution made according to proper composition that is used to hydrate our body. So here to hydrate means give enough water as well as the required ions. So here 1 decimeter cube of G1 contains 5 grams of sodium chloride. So here mass over volume of NaCl, or you can write it in words, mass volume fraction of sodium chloride. We can easily use the symbols here, M over V of sodium chloride. That is equal to mass of sodium chloride, that is the solute, and the volume of solution. Here it is G1. So here you can see the mass is 5 grams and the volume is 1 decimeter cube. So that will be 5 gram decimeter minus 3. Here can we remove the unit? No, because the mass and the volume have different units. So we have to express it using that particular unit. With that, we will move on to the next one, expressing composition of a mixture in terms of amount of moles per volume. So this is a very common unit used in chemistry. In the laboratory, when we say chemistry, even in science, we use lot of solutions, chemical reactions. So for all that, when we need to prepare solutions, mostly the composition is expressed as moles over volume. And we give a special name for this quantity or the composition. This is called concentration. I will summarize all this. This is used to express the composition of a homogeneous mixture. So this is only for solutions. Mole is the international unit for the amount of matter that I discussed before. Here the composition is given in terms of the amount of moles of solute contained in unit volume of a solution. So, amount of moles of solute contained in unit volume of a solution. The composition expressed in this way is called the concentration. In chemistry, very often concentration of a solution is expressed in terms of the amount of moles of solute contained in a cubic decimeter of the solution. If we write that, that is moles per cubic decimeter, mole dm minus 3. So, this is a unit or a way of expressing composition that is very commonly used in laboratory procedures related to chemistry. So, we will see how we can use this composition. So, I can write the values or the name as mole volume or we can say concentration. Here we don't use mole volume fraction, but we can just put a stroke there, mole over volume or concentration. So that will be equal to number of moles of the solute divided by the volume of solution. So, if there are more than one solutes, you can calculate the concentration for each solute separately. Say like G1 before, if there is sodium chloride and magnesium chloride in water, then we can calculate the concentration of sodium chloride separately, the concentration of magnesium chloride separately. We will do some examples. 2 decimeter cube solution of sodium hydroxide was prepared by dissolving 80 grams of sodium hydroxide in distilled water. So, the volume of the solution is 2 decimeter cube. The mass of the solute is 80 grams and they say distilled water. Here we use the word distilled water because these are solutions which need to be prepared in the pure form. So, distilled water is pure water, does not have any impurities. So, therefore, we mention it as distilled water. So, first we need to find the number of moles of sodium hydroxide. So, N equals mass over molar mass. So, mass is 80 grams of sodium hydroxide. You know sodium hydroxide is NaOH and N has a molar mass of 23, O has a molar mass of 16 and hydrogen has a molar mass of 1. So, when you add them together, NaOH is 40 gram per mole. So, that will give the mole value as 2 moles. Gram and gram cancels off, mole minus 1 becomes mole. Then we have to find the concentration. Concentration of NaOH. This can be written as CNaOH because concentration is the name of this particular composition. So, C is composition. So, here if I write number of moles of NaOH divided by volume of solution. So then we can write the number of moles as 2 moles divided by, here you can see 2 decimeter cube of solution. 2 decimeter cube. 2 and 2 can be simplified. 1 mole per decimeter cube. Here students, you have to remember this is the common unit. The unit that is used normally for calculations. Mole per dm cube. So I will write that here. Moles per decimeter cube is the common unit. We saw that in the previous discussion as well. But the standard international unit will be given as moles per meter cube. This is something that you have to remember. The common unit is moles per decimeter cube, but the standard international unit for concentration is moles per meter cube. Why? Meter is the standard unit for length. Therefore, meter cube is the standard unit for volume. So with that, we will do some more calculations. 2 decimeter cube of a solution contains 4 moles of sodium hydroxide. Find the sodium hydroxide concentration of this solution. So the volume is 2 decimeter cube. Number of moles of sodium hydroxide is given as 4 moles. So to find the concentration of NaOH, that is equal to moles of NaOH divided by volume of solution. That is directly given to you 4 moles divided by 2 decimeter cube. That is 2 mole per decimeter cube. That is the common unit of concentration. We'll look at another example. What is the mass of glucose required to prepare 1 decimeter cube of a 1 mole per decimeter cube glucose solution? So here we need to find the mass of glucose. So to do that, we need to know the number of moles of glucose that will be present in this solution. So here they have said 1 mole of glucose is required. Already they have given you the amount of glucose that is needed. So directly we can multiply that by the molar mass and find the mass of glucose. So first I will find the molar mass of glucose. Mass of glucose. So it's C6, so 12 into 6 plus H12 and O6. Relative atomic mass of carbon 12, hydrogen 1 and oxygen 16. When we multiply all these together and we get the value as 72 plus 12 plus 96. That will be equal to 180 and the unit will be grams per mole. Now we need to find the mass of glucose required to prepare that solution. They have given you 1 mole of glucose is required. So to find the mass of glucose, what do we have to do? You know the equation. Moles is mass divided by molar mass. So mass of glucose divided by molar mass is equal to moles. So therefore, mass of glucose equals moles into molar mass. That is equal to 1 mole into molar mass 180 grams per mole. Mole and mole minus 1 will get cancelled off. You will get the answer as 180 grams. So that is the amount of glucose that is needed to prepare a solution of 1 mole per dm cube concentration, and the volume is 1 decimeter cube. With that, I will move on to the next slide. Work out the mass of glucose that should be weighed to prepare 500 centimeter cube of a 1 mole decimeter cube glucose solution. So this is similar to the previous one. 500 centimeter cubes of 1 mole per decimeter cube glucose solution. So you know the concentration is equal to what? Moles of glucose divided by the volume of solution. So here they have given us the concentration. So that is 1 mole per dm cube. That is equal to moles of glucose we don't know. I will write it as N divided by the volume of the solution. That is 500 centimeter cube. 500 centimeter cube. But we need to have the unit as decimeter cube. So what do we do here? We have to convert the volume to decimeter cube. 1000 centimeter cubes is equal to 1 decimeter cube. I will write that here. 1000 centimeter cubes is equal to 1 decimeter cube. So if you want to convert centimeter cube to decimeter cube, you have to divide it by 1000. So here we have 500 centimeter cubes. I divide it by 1000. It becomes decimeter cube. If we rearrange that, N over 500 into 1000, that is equal to 1 mole per dm cube. So we can rearrange. N is equal to 1 into 500 divided by 1000. I am taking these two components to the other side. So 500 divided by 1000 is 1 over 2. That is 0.5 moles. Why? We have the decimeter cube here, mole per decimeter cube there. So the decimeter cube and decimeter minus 3 get cancelled off. So therefore, we get the value as 0.5 moles. Work out the mass of glucose that should be weighed to prepare 500 centimeter cube of a 1 mole per decimeter cube glucose solution. I have already found the number of moles. We have to find the mass of glucose. So now I need to calculate the mass. What is the mass? Mass is equal to moles into molar mass. Why? We have the equation mole is equal to mass divided by molar mass. You are familiar with these types of calculation. So here we find number of moles 0.5 moles into molar mass of, here we need to find for glucose. Glucose again you know is C6H12O6. So that will be 12 into 6 plus, that is carbon 12 into 6, 1 into 12 plus 16 into 6. That will be the molar mass of glucose. So if we calculate the molar mass of glucose, you will get the value as 180 grams. So here 0.5 mole into 180 gram per mole. So that will give you a value 0.5 into 180, that will be 90 grams. Why? The mole and mole minus 1 will get cancelled off. So you will get the mass of glucose as 90 grams. So here students, we have done the calculation in the reverse order. Normally we start with the mass, find the number of moles, then we find concentration. But if we want to find out how we are going to prepare a particular solution or what amount of solute is needed to prepare a solution, then we start with concentration, find the number of moles and finally find the mass of the solute. So now you all are very familiar with different types of calculations. We discussed 4 different types of compositions before concentration: mass fraction, volume fraction, mole fraction and mass volume fraction. And finally here concentration. Next we will see how we can prepare standard solutions. Preparation of standard solutions. So here you all know we are going to prepare solutions, but what are standard solutions? Normally when we say standard, we expect a certain high quality from it. So here also we need to prepare solutions which are of analytical quality or very good quality. That means we have to prepare solutions which are pure solutions, that should not have impurities in them. No other substances should be mixed in the solution, and also their concentration or composition has to be known accurately. Such solutions are known as standard solutions. During chemical experiments, standard solutions are required to be prepared. A standard solution is a solution in which the concentration is very accurately known. So that is what I told you all. Concentration is very accurately known. The relationships among the following units are very important in the preparation of standard solutions. So when we say concentrations, to find the concentration, we need to know the number of moles of the solute and the volume of solution. We don't have to always prepare volume as 1 decimeter cube because we express concentration in mole per decimeter cube. we don't always prepare 1 decimeter cube. We might need to prepare 100 centimeter cubes. We will need 2 liters, say 3.5 liters. Like that, we will need to prepare different volumes of solution with accurate concentrations. So that is why we need to know the relationships among different units. So one unit that can be used to measure volume is decimeter cube. Another unit is liters. So here 1 decimeter cube is equal to 1 liter. And 1 decimeter cube is equal to 1000 centimeter cubes. Similarly, 1 decimeter cube equals 1000 milliliters. Why 1 decimeter cubes equals 1 liter? 1 liter is equal to 1000 milliliter. At the same time, 1 decimeter cube is equal to 1000 centimeter cubes and 1 decimeter cube equals 1000 milliliter. So what is the relationship between these two? 1 centimeter cube equals 1 milliliter. So these are the units that you need to know. And also you can remember the common unit for concentration, moles per decimeter cube. And the standard unit for concentration, moles per meter cube. Only if we prepare large quantities with a large amount of solute, then we usually go for moles per meter cube. Otherwise, we stick to moles per decimeter cube. So now we will see how we can prepare this standard solution. The following laboratory equipment are required to prepare a solution of a specified concentration. I told you all before we need 2 glasswares. In addition to that, we need more materials. You can see in this first picture, this is known as a volumetric flask. Volumetric flask is used to measure volume accurately. To do that, if you look at the diagrams carefully, there are markings like this here. This says 100 milliliter. So the 100 milliliter is up to this mark. 250 milliliter up to this mark. 500, you can see the mark is somewhere here. And 1000, the mark is here. If we prepare a solution up to that mark, then it will be an accurate solution. There is a way of looking at the solution level. I will explain that when we discuss the activity. So these are the glasswares, the volumetric flask. So if we want to prepare 250 centimeter cubes of the solution, we choose this one. Depending on the required volume, we choose the volumetric flask. Then this one here is a wash bottle. We use this wash bottle to transfer the solute into the volumetric flask. Wash off the solute into the volumetric flask. Here we need a watch glass. Watch glass. And we need a glass funnel. Now watch glass is to weigh the solute substance. And from the watch glass, using the wash bottle through the glass funnel, we transfer the solute into the volumetric flask. dissolve it with a small amount of water, and then we fill water to the correct mark, so that we have the accurate amount of solute and the accurate volume of the solution. So that means we have a solution with accurate concentration. So that becomes a standard solution. Let me move on to the activity. Activity. Let us study how 500 centimeter cube of a 1 mole per decimeter sodium chloride solution is prepared. So to do this, we know the volume that we need to prepare. We know the concentration of the solution. But to prepare the solution, we need to know the mass of the solute. First, the mass of sodium chloride required for this should be calculated. I'm sure you can remember the calculation. We do the calculation in the reverse order. Start from concentration, find the moles, and then find the mass of the solute. You can also try it by yourself first. Now I will do the calculation. So concentration is what? Moles of solute divided by volume of solution. So if we substitute the values, we know the concentration. 1 mole per decimeter cube. And don't know the number of moles, so I use the symbol N. We know the volume of solution 500. Do we only write 500? No. We have to divide it by 1000 so that it becomes decimeter cube. Here, this can be rearranged as N over 500 into 1000 decimeter cube. So the same thing. We need to find the number of moles. So I will rearrange the equation again. Number of moles is equal to concentration 1 mole per decimeter cube. And we have the volume 500 divided by 1000, and that is also decimeter cube. So if we cancel off the units and simplify the equation, we will get the value as 0.5 moles. So we have found the number of moles of sodium chloride that should be present in the solution. Now we need to find the mass of sodium chloride. How do we do that? To find the mass, we need to write the equation mass over molar mass is moles. So if we rearrange, mass is equal to moles into molar mass. So number of moles is 0.5 into what is the molar mass? It is sodium chloride. So normally for y'all, for calculations, they will give you the molar masses. I will write it here. Sodium 23 and chlorine 35.5. So when we calculate, it will be 58.5 grams per mole. So we have to substitute that value there. The molar mass of sodium chloride, because that is NaCl. I have added the two values, 58.5. So 58.5 grams. If we calculate the value there, this has to be 29.25 grams. 0.5 into 58.5 grams. 29.25 grams. So that is the mass of sodium chloride that we need to weigh. So first, when we need to prepare the solution, we need to calculate the mass of the solute that is needed. We know the volume of the solution and we know the concentration of the solution. Now we will see what we have to do next. These are the materials that are required for this activity. You can identify this. If we want to prepare 500 milliliters of the solution, so we need to use a volumetric flask. And here the volume has to be 500 milliliters. Then we need a triple beam balance or 4 beam balance. Triple beam or 4 beam balance to weigh the solute accurately. As I told you all, we need a watch glass to weigh the solute and a wash bottle containing water. With what water? Do we use the normal water or the tap water? No, we have to use distilled water. So here we need distilled water. Why? We are preparing standard solutions where the concentration has to be accurate. Then we need a glass funnel. So now these are the things that we need. Now we have calculated, we need 29.25 grams of, here you can see 29.25 grams of sodium chloride. I will write that also here. 29.25 grams of sodium chloride. We have to weigh this first. We need a clean watch glass and the triple beam balance. We place the clean watch glass on the triple beam balance. Weigh the watch glass. Find the mass of the watch glass. In addition to that, let's say the watch glass weighs 40 grams. Then we need to weigh 29.25 grams of sodium chloride. So then we add this 29.25 grams with 40 grams. That will give you a value of 69.25 grams. We set the triple beam balance to 69.25 grams. Then we add sodium chloride little by little until the balance becomes stable, until it reaches equilibrium and points to 0. At that point, we would have measured 29.25 grams of sodium chloride. So we have the solute ready. Then we have to hold the watch glass with the funnel into the volumetric flask. I will show how to do this when I do the activity. And using the wash bottle, we have to wash off all the solute. Make sure that we don't leave any solute in the watch glass because we are preparing accurate concentration. So we have to transfer all the solute into the volumetric flask. So we transfer everything, then we close the lid of the volumetric flask, mix and dissolve the solute well, and then after placing the volumetric flask on a table, with your eye level, transfer and make the volume of the solution to 500 centimeter cube. So we needed 29.25 grams and we need 500 centimeter cube solution. Those are the steps. Here you have to remember, students, we have to use all very clean glassware so that there are no impurities, and we use distilled water. Also, the sodium chloride that we are going to take should be of good quality. If we use the sodium chloride, the table salt available at home, that may not be pure. Why? When we use it in our day-to-day life, there are possibilities of edible impurities getting mixed there. Not the poisonous one, but anything related to food. So that cannot be used in the lab to prepare standard solutions. So now I will go through the method again. Weigh 29.25 grams of sodium chloride very accurately onto a watch glass using a laboratory balance, a triple beam balance, 4 beam balance, or we can even use a digital chemical balance. Select a clean 500 centimeter volumetric flask. Remove its stopper and place a clean funnel. Transfer the weighed sodium chloride on the watch glass completely through the funnel using the wash bottle. Wash the surface of the watch glass and the inner surface of the funnel and transfer the washings into the flask. Washings means when you transfer water, put the water onto the sodium chloride, it gets washed and goes into the volumetric flask. Add about 2/3 of the required volume of water. Stopper the volumetric flask. Shake the flask so that all of the sodium chloride dissolves well. When you say shake, you don't shake it randomly. And you have to make sure the stopper is closed. Otherwise, some of the solution, the solute and the solvent can spill out. So we won't get an accurate solution. After all the salt is dissolved, add water carefully, keeping the eye at the level of the volume mark of the flask. Stop adding water when the meniscus is at the position of the mark. Stopper the flask and mix again. I will tell you all what these are. Now we will look at this again, but here if this is the volumetric flask, this is the volume mark, the meniscus is the water level like that. The bottom of this curve has to be in line with the volume. So up to this we have to fill water so that you get 500 centimeter cubes of the solution accurately. So this is the meniscus. Now to find the meniscus, if this is the volumetric flask and if this is the volume mark, your eye has to be in line with the mark. If you have it here, and you look like this, the water level will be at a different place, the mark will be at a different place. The same way, if the meniscus is up, the mark is up, you can't see the water level clearly. So, it has to be with the eye level. So, we place the volumetric flask on the table. You have to adjust yourself so that your eye is with the volume mark, and make sure that the meniscus is seen this way. Until that point, we have to add distilled water. Then we stopper the flask again and we mix it well so that we get the proper accurate solution. So students, when we discussed and we did the calculation, we were supposed to measure 29.2 grams of sodium chloride. But in the lab, I have a 250 centimeter cube volumetric flask. So according to this activity, we are supposed to measure or weigh 29.25 grams of sodium chloride in order to prepare 500 centimeter cubes of the solution. But since we have a 250 centimeter cube volumetric flask, I will have to weigh half of this weight. So here I will be using a 250 centimeter cube volumetric flask. Therefore, the amount of sodium chloride that needs to be weighed. Now for 500 it's 29.25. So if we divide it by 2, that will be equal to 14.625 grams. So here, since I am going to demonstrate the way of preparing standard solutions, I am going to weigh 14.6 grams of sodium chloride and prepare 250 centimeter cubes of the solution. So now that you have understood the steps clearly, you need to watch carefully how the solution is prepared, the steps involved in it. Now we will go to the lab and prepare the standard solution. Okay students, so now I am going to prepare a standard solution of sodium chloride. To do that, I have a wash bottle with distilled water, a volumetric flask. You can see it is a 250 centimeter cube volumetric flask. And here you can see the volume mark. We have to fill water up to this point so that we get exactly 250.00 centimeter cubes of the solution. Then I have the funnel to help us to transfer the solute into the volumetric flask, and also the solute is sodium chloride. We need to take 14.6 grams of sodium chloride in order to prepare 250 centimeter cubes of 1 mole per decimeter cube solution of sodium chloride. And as you know students, we have to weigh the solute accurately. So to do that, I have the triple beam balance here. With the watch glass, I have balanced it to 0. So you can see the 0, the balance is at the rest. It's pointing to 0 with the watch glass. Now I need to set the value to 14.6 grams. So here 14.6 grams. So to that, if I add the sodium chloride, then we will be able to weigh 14.6 grams. We have to weigh the exact amount of sodium chloride. Now you can see the scale coming to a balance. If it points to 0, that means we have weighed 14.6 grams. So now I have the volumetric flask, a clean one. I will set everything so that I can easily transfer the substance. So here I have the funnel. I'll hold it slightly above the mouth of the volumetric flask, and to that I have to hold the solute containing watch glass in this manner so that I can easily dissolve and transfer all the sodium chloride into the volumetric flask. So that is the use of the wash bottle here. We can make sure that we transfer all the solute into the volumetric flask. So here I have transferred the solute, everything from the watch glass, and I wash it with more water to make sure that all the solute is dissolved here. Now I have transferred all the solute into the volumetric, and also I wash the funnel again to make sure that all the solute is transferred into the volumetric flask. Now what I have to do is I have to add about 3/4 of the volume of water. Okay. Now I close the lid again just to make sure it's clean. What do? We hold the volumetric flask in this manner. Always you have to have a hand under the volumetric flask, and by swirling it, we can dissolve the solute. It has to be a swirling motion so that the solute dissolves completely. We shouldn't turn it upside down. So here you can see the solute dissolving. If we keep on swirling it like that, the solute will dissolve completely. I think all the solute is almost dissolved now. So that the solute is completely dissolved. Now I will make the volume up to the volume mark. So again I'll remove the lid and add more water. Up to a certain point you can quickly add water. Now it's almost closer to the volume mark. So my eye level has to be along the line, and here I have to make sure that I add the correct volume of water. You can see the meniscus here, students. The curve, the bottom line of the meniscus has to be in line with the volume mark in the volumetric flask. So I'll again make sure that I have added the correct volume, and now I can close the lid, and I have prepared the standard solution of sodium chloride. So students, now I have added the correct volume of water, and I have to make sure that the solute gets distributed throughout the solution. So to do that, again we have to mix the solution, but we have to be careful that the solution or the solvent doesn't escape from the volumetric flask. So when I mix it well like that, the solute gets distributed evenly. So we have a solution where the concentration is uniform. So that means we have prepared a standard solution with a known concentration. So once that is done, you can't leave it like this, because there are instances where many people work in the same lab and you might need to make more than one solutions which look the same. So then we have to put a label for the solution so that we can identify the solution easily. And what do we include in the label? We have to write the solvent, the solute, the name of the solution and the concentration of the solution, as well as the date on which the solution was prepared. And to make it more clear, if there are many people working in the lab, we can also include the name of the person who prepared the solution. So then the label will have all the necessary information. So students, keep it in mind that when we prepare a standard solution, the measurements have to be accurate, all the glasswares have to be clean, and once we do the preparation, we have to label the solution. So here I have the standard solution of sodium chloride. I have to have a label on this. Okay students, so you saw how you're supposed to handle the different types of glassware and equipment when preparing a standard solution. So here I have given some considerations and things you should remember under discussion. So here as an example, if we consider the solution that we prepare. So you can remember students, we did the calculation for 500 centimeter cubes of solution. But we had a 250 centimeter cube volumetric flask. So accordingly, I weighed the solute, that is sodium chloride. So here in this label, what do we need to include? Name of the solute and the solvent. So here we took sodium chloride, that was the name of the solute. And what was the solvent? Normally they use physical states, but you all don't need to put it. I'm using it here. Solid means you know that sodium chloride is solid. So S. Then water was the solvent. So that is a liquid. Then what do we need to write? The amounts of the solvents and the solute as well as the solution. So how much of sodium chloride did we take? We took 14.2 grams of sodium chloride and we had to prepare 250 centimeter cube of the solution. So we had included the amounts of the solvents and the solution used with their unit. So here you can see gram and centimeter cube. Then what do we need to write? The name, concentration and the date of preparation. So to write down the name of the solution, this is sodium chloride solution. Sodium chloride solution. Then the concentration was 1 mole per decimeter cube. So when we took 14.2 grams into 250 centimeter cubes, the concentration becomes 1 mole per decimeter cube. In addition to this, I have told you all during the activity, if you are working in a common lab where many people prepare different solutions, then it is better to include the name of the person who prepared the solution. So you will have to include your name here and also the date of preparation. So this is what you need to include in a label. So once you prepare the standard solution properly, you write the label and immediately paste it onto the volumetric flask so that there will be no confusion. Now, we will look at those. When preparing a solution of a specific concentration, following factors should be taken into consideration. Cleanliness of all the equipment used. I have discussed this with you all before also. The cleanliness is very, very important. Why? We are preparing solutions of accurate concentration. So, if it is sodium chloride, it has to be only sodium chloride in distilled water. If the watch glass had a small amount of magnesium chloride in it, then the solution also will have magnesium chloride. So, then it will not be a pure solution. So, you need to have very clean equipment. Weighing the solute accurately. If we say 29.25 grams of sodium chloride, it cannot be 29 grams or 29.5 grams. Those are incorrect. It has to be 29.25 grams. So, accurate weighing of solutes. Washing well and transferring the substance sticking onto the watch glass and the funnel into the flask. So, that is why we use that particular setup to transfer all the solutes without spilling any, without leaving any in the watch glass. Everything has to be washed into the volumetric flask so that we have again an accurate concentration for the solution. Use the correct technique for mixing. As I told you, you can't just randomly shake the volumetric flask. There is a way of mixing the solution so that nothing spills off. Adjusting the final volume. That again, I told you all how you should observe the meniscus. I will draw it again just to confirm it for you all. This is the volume mark. And that is the meniscus. And your eye has to be at the same level. Along the eye level, you should have the volume mark. And we fill volume or the liquid up to that point. Prevention of the entry of impurities into the solution. So, as I told you before, even a small amount of magnesium chloride, that is also a chemical substance that is needed for other purposes. But when we prepare sodium chloride, if there is magnesium chloride, that it's also an impurity. It doesn't have to be dirt or anything. Any other substance is considered as impurity. So, we have to make sure that there are no such impurities when we prepare the standard solution. So, students, these are the considerations what you have to keep in mind and follow when you prepare a standard solution. With that, we will move on to the next activity. Divide the class into 4 groups and prepare the 4 solutions given below using the correct method. So, you all are supposed to do this as groups. 250 centimeter cube of 1 mole per decimeter cube sodium chloride. 100 centimeter cube of 1 mole per decimeter cube glucose. 500 centimeter cube of 1 mole per decimeter cube urea. 250 centimeter cube of 1 mole per decimeter cube copper sulfate solution. In the solutions you have prepared, name the solute and solvent. Indicate the amounts of the solvents and the solutions used with their units. Indicate the name, concentration and the date of preparation. Give examples for the instances of preparing solutions in everyday life. So this is an activity where you will learn to prepare the solution accurately, weighing the solute, preparing the solution by transferring it into the volumetric flask, making the correct volume. So before you do that activity in the lab, what is the calculation you have to do? You should know the mass of all these solutes that you need to weigh. So first I will show you all how you can do the calculations. But before I show you the calculation, I want you to do it by yourself. In case you can't find the molar masses or the relative atomic masses of the elements, I will write it here. Sodium 23, chlorine 35.5, then carbon 12, hydrogen 1, oxygen 16, copper is 63, and we have sulfur also. Sulfur is 32. So using all these values, I want you to try and calculate the mass of these solutes. After that, I will do the calculation and show you. So students, now we need to do the calculations. There are 4 different solutions. So I am not going to write the equation again and again. So for the initial calculation, I will write all the equations. What is the equation for concentration? Concentration is equal to moles of solute divided by volume of solution. This has to be in moles and decimeter cube. Then what do we do? Once we find the number of moles, we have to find the mass. Mass over molar mass is what? Moles. So if we rearrange, mass is equal to molar mass into moles. These are the equations that we need. So first I will do the first calculation. Let us check the solution. First one is 250 centimeter cubes of 1 mole per decimeter cube solution. So 250 centimeter cubes, 1 mole per decimeter cube of sodium chloride. So what do we do first? We have to substitute the values to find the number of moles first. So number of moles of NaCl. The concentration is known to us, 1 mole per dm cube. And what is the volume? We need to prepare 250 centimeter cube. So we need to multiply by 250. Do we use it directly? No. We have to divide it by 1000 so that we get the concentration as decimeter cube. So you will get the number of moles. When you simplify 1 into 250 over 1000, we get 1 over 4. That is equal to 0.25 moles. What is the next step? Find the mass of sodium chloride. So, mass of NaCl, that is 0.25 moles into molar mass. What is the molar mass of sodium chloride? I am sure you would have found it as 58.5 gram per mole. We calculated this before as well. Sodium 23, chlorine 35.5. So when we multiply it by 58.5 grams per mole, you get the answer as, if I divide 14.625 grams. So we have found the mass of sodium chloride that is needed to prepare the solution. So I'll again go to the next solution, that is 100 centimeter cubes of 1 mole per decimeter cube glucose solution. 100 centimeter cubes of 1 mole per decimeter cube. So we need 100 centimeter cubes, 1 mole per decimeter cube, and it is glucose. So first I will calculate the molar mass of glucose. You know the chemical formula C6H12O6. So carbon is 12 into 6 plus hydrogen 1 into 12 and oxygen 16 into 6. If you add them together, 72 plus 12 plus 96. That will be equal to 180 grams per mole. That is the molar mass of glucose. So if we do the calculation here, first we need to find the number of moles. N of glucose. To do that, we multiply the concentration by the volume divided by 1000, so that we convert the volume to decimeter cube. So here we have the value as 100 divided by 1000, 0.1 moles. Now I have to find the mass needed. So here mass of glucose will be what? Number of moles into molar mass. So that is going to be 0.1 mole into 180 gram per mole. That is going to be 18 grams of glucose. So I am sure you did the calculation correctly. Now let me check the third solution. The third one, 500 centimeter cube of 1 mole per dm cube urea. You can see the chemical formula of urea here. CONH2 twice. So then 500 centimeter cubes of 1 mole per decimeter cube. We need 500 centimeter cubes, 1 mole per dm cube of urea. So urea is CONH2 NH2 twice. I will calculate the molar mass first. Carbon 12, oxygen 16, nitrogen 14, but there are 2 nitrogens, and hydrogen 1, there are 4 hydrogens. So when we add them together, 12 plus 16 plus 28 plus 4. So that will be 60 grams per mole. So if I do the calculation, first we need to find the number of moles of urea. What do we do? Concentration into volume. What is the concentration? 1 mole per dm cube. And what is the volume? 500 divided by 1000 decimeter cube. So then you will get the value as 0.5 moles. What is the next step? To find the mass. Mass of urea is equal to what? Mole into molar mass. So that is going to be 0.5 moles into, we have found the molar mass, 60 gram per mole. So we get the value as 30 grams. Mole and per mole gets cancelled off. You get the unit as grams. So now we have calculated the mass of 3 different solutes. The fourth one. So here we have 250 centimeter cube of 1 mole per decimeter cube copper sulfate solution. 250 centimeter cube, 1 mole per decimeter cube solution. 250 centimeter cubes of 1 mole per decimeter cube copper sulfate solution. So if we find the molar mass, copper 63, sulfur 32, oxygen 16, but there are 4 oxygens. So when we add them together, 63 plus 32 plus 64. So that will be 159 grams per mole. What is the next step? We find the number of moles of copper sulfate needed. Number of moles of copper sulfate. What is that? The concentration 1 mole dm cube into volume 250 divided by 1000, and that will be in decimeter cubes. So when we simplify that, it becomes 0.25 moles. After that, what do? We need to find the mass of the copper sulfate needed. So to find the mass of copper sulfate needed, I will calculate mass of CuSO4 moles into molar mass 159 gram per mole. And when here it has to be 0.25 moles. You all have to be very careful, students. When we substitute values, you have to look at the calculated value properly and substitute the correct value there. So 0.25 and 0.2 would have given you different answers. And here we are preparing standard solutions. We have to be very careful. 0.25 moles into 159 gram per mole. Then you will get the value as 9.75 grams. So that is the mass of copper sulfate that is needed to prepare the solution. So students, I have shown you all the calculations. I am sure you all did the calculation correctly and you saw how you are supposed to prepare the standard solution. I am sure you can do that correctly by yourself, individually or as groups. And also at the end of preparation, what do? We have to put a label. What do we include in the label? The name of the solute, the solvent, the concentration, the date prepared. If you like, since you all are doing it as different groups, you can even write the name of your group so that you know who prepared which solution. So that is how we prepare standard solutions in the laboratory. Now I will move on to the assignment. Make a list of instances in which solutions of very accurate composition should be prepared. For example, they have given preparation of saline solution. You all know what saline solutions are. When a person falls sick, if the person gets dehydrated, in order to hydrate, that is to give enough water, normally a saline solution is given to the person. Otherwise, saline solutions can be used to clean wounds also. So, this is a solution which is made up of water and salts in certain composition. Water, that is pure water, and salts mixed together so that a person will be hydrated properly. There, you can't put too much of salt. That can increase the thirst of the person. You all know from experience, when you eat salty food, you feel like drinking more water. You become more thirsty. So, the same way, if the saline solution contains too much of salt, the person will feel more and more thirsty. That is not good. The same way, if there isn't enough salt, then there will be only water, not enough salt in the body. So, therefore, the saline solution has to be prepared accurately according to the prescription. So, that is where we need to prepare very accurate composition. Now, they have told you to make a list of instances in which solutions of very accurate composition should be prepared. We have discussed some before. Mixing weedicides, mixing insecticides. Those were some examples given to you. I will just list them out here. Mixing weedicides. You all already know what these are. Insecticides. What else? When preparing medication according to prescription. So here another thing, when preparing medication. These are all what we discussed before when preparing medication. The same way, if we are painting the walls of the house, what if we put too much of solvent, that is if we mix too much of water to emulsion paint? The paint will be very dilute, it will be thin. You won't get the correct color. And sometimes if you don't mix it properly, you won't get even painting. The same way, if you don't put enough water, the paint will be too thick, then it will be difficult to paint the wall. So there also you need to mix solutions very accurately in the proper manner. So here I can include that as well, mixing paint. Or even in the industrial process, when they prepare paints to get the proper color, like we discussed in the first slide when we started the composition of mixtures. You have to be very careful when preparing these types of solutions. So students, these are a very few examples I have given to you. Similar to this, you can identify and prepare a list of solutions that need to be prepared with accuracy. So with that, I will move on to some questions. A solution was prepared by weighing 17 grams of sodium nitrate very accurately, dissolving it in a 200 centimeter cube volumetric flask and diluting with water up to a final volume of 200 centimeter cube. What is the concentration of this solution? So as you know, initially we add a little bit of water, about 3/4 of the volumetric flask, dissolve the solute and make the volume up to the mark. That is why they have said diluting with water up to the final volume. When we add more water, the concentration decreases. That is why we call it diluting. The process of diluting or dilute solution means there is more water. Concentrated solution, more solute, less water. That is if the solvent is water. So here we need to find the concentration. So I will say concentration equals what? Moles over volume. To do that, what do we need to know? We need to know the moles of the solute. Moles of, here we use sodium nitrate, NaNO3. What is the mass? 17 grams. We divide that by molar mass. What is the molar mass? If it is sodium nitrate, I will do it on the side. NaNO3, 23 plus 14 nitrogen, oxygen 16 into 3 is 48. So you add them together, you get the value as 85 grams. So that is the molar mass of sodium nitrate. Then if I substitute the value here, mass divided by molar mass, 85 gram per mole. And I will get the value as 1 Yes, 1 over 5. So that is going to be 0.2 moles. Gram and gram cancel off, you get the unit moles. Then what do? We need to find the concentration. So to find the concentration, that is moles over volume. What is not the number of moles? 0.2 moles divided by the volume. Volume is what? We need 200 centimeter cubes of the solution. 200, but I need to convert it to decimeter cube. So I rearrange and write it as multiplication. I have showed you all this before. So you will get the answer as, you can simplify the zeros. 2 and 0.2 become 0.1. 0.1 into 10 is 1 mole per dm cube. So that is the concentration of sodium nitrate solution. With that, I will move on to the next question. What is the mass of potassium carbonate required to prepare 500 centimeter cube of a 1 mole per decimeter cube potassium carbonate solution? I am sure you can answer this question by yourself first. Now I will do the calculation. So we need to find the mass. To find the mass, we need to find the mole first. So here concentration equals moles over volume. That means here the concentration is given to you 1 mole per decimeter cube. We don't know the number of moles. I'll put it as N, and the volume is 500 centimeter cube. So obviously I have to convert it to decimeter cubes. If we rearrange 1 mole per decimeter cube into 500 divided by 1000 decimeter minus. So here when you simplify the two values, you get the value as 0.5 moles is equal to N. We have found the number of moles. What do we need to find? We need to find the mass of potassium carbonate. We need to find the mass. So before I find the mass, I want to find the molar mass of potassium carbonate. So here if we write the chemical formula K2CO3, potassium will be given to you as 39. So 2 potassium plus carbon is 12 and oxygen 16. When we do the calculation, we get the value as 78 plus 12 plus 48. So that is 138 grams per mole. That is the molar mass of potassium carbonate. So now we have to find the mass of potassium carbonate that is required to prepare the solution. So here if I do the calculation, mass of potassium carbonate, that is going to be 0.5 moles into 138 gram per mole. So that will give you a mass of 69 grams. 0.5 into 138. 69 grams. So we have done this calculation as well. The next one. A solution of 1 decimeter cube is prepared by dissolving 12 grams of urea in distilled water. Find the concentration of this solution. So here, in order to find the concentration, you need to find the number of moles. To find the number of moles, you need to know the molar mass of urea. So if we find the molar mass of urea, CO, NH2 twice, we have done this before also, carbon 12, oxygen 16, nitrogen 14, but there are 2 nitrogens, and hydrogen 1, there are 4 hydrogens. So if you add all of these, 28 and 28, 56 plus 4, 60 grams per mole. That is the molar mass of urea. Then what do? We find the moles of urea, mass over molar mass. That is 12 grams. Here it's given to you 12 gram divided by 60 gram per mole. So 12 over 60 is 1 over 5. So you get the value as 0.2 moles. Then we have to find the concentration. We find the concentration equals moles divided by volume of solution. Here moles of the solute, volume of the solution. 0.2 moles. What is the volume? 1 decimeter cube is prepared by dissolving 12 grams of urea. So here already we have the volume in decimeter cube unit. So we don't have to do a unit conversion. That will give you the concentration as 0.2 moles per decimeter cube. That is the concentration of urea. Then I will move on to the next question. To a 250 centimeter cube volumetric flask, 18 gram of glucose was transferred and distilled water was added until the total volume of the solution was 250 centimeter cube. What is the concentration of this solution? So here we need to find the concentration. To do that, we need to find the molar mass. Why? We need to calculate the number of moles. But we have already calculated the molar mass of glucose. If you can remember, C6H12O6 will be equal to 180 grams per mole. Students, you all can do the calculation and check the value. So here to find the number of moles equals mass over molar mass. Students, I am repeatedly writing the equations so that you remember the equations carefully. And also when you do a calculation in the exam paper, write the equation and substitute so that there is less chance of making a mistake. Mass over molar mass. So what is the mass of glucose? 18. So we have to substitute. Mass is 18 grams and the molar mass is 180 grams per mole. So you will get the number of moles as 0.1 mole. Then what do? We need to find the concentration. So concentration equals number of moles, 0.1 mole divided by what? The volume. But the volume is given as 250 centimeter cube. You can either divide it by 1000 here, or you can directly multiply by 1000. So the volume becomes decimeter cube. If we do the calculation, 250 and 1000, you can simplify 4. 4 into 0.1, 0.4 moles per decimeter cube. That is the concentration of glucose in this solution. So then I will move on to the next one. Here this is something that you have to remember for your attention. As a safety measure, when diluting concentrated solutions, always the acid should be added to water. It is because the dilution of concentrated acids is highly exothermic. Exo means out. Thermic refers to heat energy. When you dilute acid solutions, heat is given out. So because of this evolving of heat, there can be explosions. That is why they say dangerous. So if you pour water into acid, a lot of heat can be given out at once. That can become dangerous. So what we do is we take a container. So here we have a beaker. If we want to add 25 centimeter cubes of the acid to water and prepare 500 centimeter cubes of solution, what we can do is first we can take 400 centimeter cube of water, add the 25 centimeter cube of acid in small quantities. So that heat is not given out at once. Once you transfer all the acid, then you make the volume to the final volume. Make the final volume. Let's say 500 centimeter cube. So this is the correct way of diluting acid solutions. With that, I will move on to the next one. When n moles of a solute are dissolved in a solution of volume V, its concentration C can also be found using the following equation. C is the concentration. You know the equation, number of moles divided by the volume of solution. Number of moles of solute divided by the volume of solution. So C equals N over V. Concentration equals number of moles of solute over volume of solution. When N is in moles, MOL is the unit, and V is in cubic decimeters, concentration C is given in moles per cubic decimeter. We have been using this. Using the above equation, solve the previously studied worked examples to calculate the concentration. I will do one example for y'all. We have calculated and finished all the questions given before. So you can do it again using this equation. So I'll do the first example. A solution was prepared by weighing 17 grams of sodium nitrate, very accurately dissolving it in 200 centimeter cube volumetric flask and diluting with water up to a final volume of 200 centimeter cube. What is the concentration of this solution? So first we need to have the molar mass of sodium nitrate, 23 for sodium, nitrogen is 14, oxygen 16 into 3. So we get the value as 23 plus 14 plus 48. That will be equal to 85 grams per mole. So then we need to find the number of moles. For that also we can use the equation. Mass over molar mass. So that is 85 grams. As I told you before, students, you have to be careful when substituting the values. What do we write as mass? The mass that is given to us. So that has to be 17 grams and the molar mass is 85 grams per mole. So when you simplify that, it becomes 1 over 5. That is 0.2 moles. We have done this before. So then to find the concentration, we use C equals N over V. N is 0.2 moles and volume is 200 but centimeter cubes. Therefore, we need to multiply by 1000 to convert it to decimeter cube. So, 0.2 divided by 200 into 1000. You get the concentration as 1 mole per decimeter cube. Mole per decimeter cube. Zeros cancel off and when we simplify, the answer is 1 mole per decimeter cube. So I am sure students, we have done a lot of calculations. So these are again the same calculation being repeated with the equations of symbols. So using the symbol without writing the equation in words, try and do the calculations again. It will give you lot of practice. So with this, I have come to the end of discussion on composition of mixtures, preparing solutions and calculations related to concentration, which is the most common unit of composition in chemistry. After this, I will be moving on to a new topic, separation technique.